Hello there, welcome back. We are still in chapter 6, the thermodynamics of redox reactions. In this knowledge clip, we are going to talk about the relationship between the electrochemical cell potential and the Gibbs free energy change of a redox couple. Moreover, we're going to introduce the standard hydrogen electrode, which allows us to put a reference point for electrochemical cell potentials. Last time we introduced the concept of the electrochemical cell. The electrochemical cell is composed of an anode and a cathode. In the anode compartment, there is a solution that contains a chemical that has a low electrochemical potential, such as zinc, for instance. Zinc is being oxidized at the anode and thereby donates its electrons, which then can flow through this wire to the cathode, the positively charged electrode. The cathode is surrounded by a solution that contains a chemical with a higher electrochemical potential, such as copper. The copper can then be reduced with the electrons that came from the anode at the cathode and, for instance, form a solid precipitate on the surface. In order to maintain electroneutrality, the negatively charged counterions in the solution must be able to travel from the cathode regions to the anode regions, which is facilitated via this salt bridge. Now we are going to learn that the voltage that you can measure here between anode and cathode is actually equivalent to the work of moving the charges. Let's picture a cathode and an anode here, and a charge Q in between. When you have two electrodes, you will have an electric field E in between those. And here you see the electric field lines. The electric field is a vector with X, Y, and Z components. That's why we put an arrow on top of the E here. So the electric field has the unit newtons per coulomb, newtons per charge. It can also be expressed in volts per meter. The charge, on the other hand, has the unit coulomb. The force that we would like to know now of moving the charge has the unit newtons. Now you can easily see that that force is equal to the charge times the electric field. When you look at the units, charge is coulomb times electric field is newtons per coulomb. The coulombs cancel out and you only have newtons left. So that is the force. The work, on the other hand, of moving the charge has the unit of energy, joules. And here I give you an infinitesimal small change of the energy or work that is performed when moving this charge Q along the electric field lines. That is, according to Newtonian mechanics, simply the force times the distance. Distance is given as r and has the unit meter. So you see, force times distance is Newton times meter is joules. How do we express the force? We've just done it. We plug in the relationship for moving the charge along the electric field, and then we get here for the force Q times E, and multiply it again with the distance over which we move the charge now along the electric field lines. And now take a look. Here's a negative sign. Why do we put that? If the charge is, say, negative, then it would be a minus Q, and the minus of the Q and the minus in front of here, they would neutralize each other and it would be positive. Now think of it. If you have a negative charge here and you want to move it towards a negative electrode, then you have to perform work. That means dW must be positive. You have to externally add work to the system. On the other hand, if the charge is positive, that means the minus here will stay, then the work change will be actually negative, which means the system is actually giving out work, just in agreement with our nomenclature for the signs of work. So we now call that work that is performed also the potential energy that the charge gains. So say if we now move a negative charge towards a negative electrode, then it will increase its potential energy, right? Because it's just like a spring. If you compress a spring and then it is compressed, it will have a higher potential energy. The same goes for the charge. If we move it against a negative electrode, a negative charge, then it will increase its potential energy. If you let go of it, it would basically fly away because it has a certain potential energy and wants to lower that potential energy. So this was the infinitesimal small change of the work. To calculate the total amount of work that is to be performed in moving the charge from one point to the other, we can also relate that to the total amount of potential energy change that we get. What we need to do is we simply need to integrate the infinitesimal small potential energy change from position 1 of the charge to position 2 of the charge. And that is just now done by plugging in this expression for the potential energy change into the integral, as you can see here. And now we move from position 1 to position 2, which is expressed by the r, the distance that the charge travels. So now we have an expression for the total work or the total potential energy change of that charge, and we can now normalize it with the charge itself. Then basically we call that the electric potential difference, and that potential difference has the unit volts, and volts is also joules per coulomb. And now you see the meaning of this title. The voltage is just the work of moving charges. So you see, volts is joules per coulomb. It's the work in joules for moving a single charge, or at 1 unit of charge, 1 coulomb. So plugging in again everything for this expression, but now we can take out the charge itself from the integral, gives this expression for the potential energy change that it needs to be that comes with the moving of the charge. Now, what is charge? One electron, for instance, it has a negative charge, as we know, and we call it the elementary charge E, or the electron charge here. The value has been measured to be 1.6 times 10 to the negative 19 coulomb, a very small number since it's just one electron. On the other hand, the charge of 1 mole of, for instance, electrons is given by the so-called Faraday constant. The Faraday constant has this beautiful F with these nice squirrels at the sides, and that value is obtained by multiplying the Avogadro constant, so how many particles per mole, times the elementary charge. And you can see the number is significantly larger than the elementary charge since it corresponds to 1 mole of charges. So now let's talk about how the reduction potentials of an electrochemical cell are related to the free energy changes of the redox reaction. So here in this electrochemical cell, we have an electrode on the right that has an electric potential, and an electrode on the left that has an electric potential as well, but for the left. So per definition, the difference between the electric potential of these two electrodes is the potential on the right side minus the electric potential on the left side. In this case here, actually, the electrons flow from left to right, and the electric potential of the electrode on the right is larger than the electric potential of the electrode on the left. Opposite situation here. Here the electrons flow from the right to the left, and in that example, the electric potential on the right side is smaller than the electric potential on the left side. So you can see, electrons always flow from low to high potential, from, for instance, the zinc to the copper electrode, because the zinc has a low potential and the copper has a higher potential. So that's actually confusing, because we have learned before that for the chemical potential, it states that molecules flow from high chemical potential to low chemical potential. Here it's the opposite. Electrons flow from low chemical potential to high chemical potential. The reason is historically the potentials were defined based on the movement of positive charges. For positive charges it's true, like for the chemical potential, a positive charge moves from a high potential to a low potential, but an electron moves to a high potential. So at standard conditions, of course, again, we can express the electrochemical potential just with the standard state at 1 mole per liter and 298 kelvins and 1 atmosphere pressure as the difference between the electrical potential on the right minus the electrical potential on the left, both at standard states. So now we relate the free energy G to the cell potential. The work, as we have seen, is equal to the amount of charge that has been moved times the voltage, right? We've seen this on the previous slide. So we can now express that work with the amount of moles that are being moved, moles of electrons, times the Faraday constant, and you see it has the unit coulombs per mole, and when we multiply it with the moles, then we get just coulomb. So this will just be coulomb, that will be the charge that is moved, and then we just multiply it with the voltage, which is the electrochemical cell potential. That gives the work, and that work is equal to the free energy difference between the redox couple that we have, say zinc and copper, right? There's a difference in their Gibbs free energies, and that's just simply the work that is required to move the charges between the redox couple. As simple as that. Now, of course, again, we can express this at standard conditions. Then we just need to use the electrical potential at standard conditions. Now, we can rearrange the equation so that we can actually obtain the electrochemical cell potential with the Gibbs free energy change, as it is done in this equation. And you know from previous knowledge clips, the Gibbs free energy change can be related via this equation to the equilibrium constant K. So measuring the cell potential in a redox cell allows us to actually obtain the equilibrium constant K. So now let's take a look how electrochemical potentials are measured. Delta E potential measures differences in electrochemical potentials, right? It's actually not possible to measure absolute values for the electrochemical potentials of any chemical. It's just like with the enthalpy. It's not possible to measure absolute enthalpy values, but always only differences, delta H values. But you need a standard state to where you say the enthalpy, or in this example, the electrical potential is 0. And that's the standard hydrogen electrode. The standard hydrogen electrode is actually not made out of hydrogen, but of platinum. So this platinum is an inert metal. It does not undergo oxidation or reduction. And then there's a solution of hydrochloric acid around the platinum electrode, and at the same time hydrogen gas is bubbled through that solution. So now the protons in that solution, they are at a standard state of 1 mole per liter. That's the concentration in here. And they can react with electrons that come from the electrode to form hydrogen gas at 1 atmosphere pressure, right? So now the potential of this standard hydrogen electrode, I mentioned it already, it is just defined to be 0 volts. It's not really 0 volts, but it is defined as 0 volts. So you can then connect any other electrode to this standard hydrogen electrode, for instance a silver electrode, and then measure the potential of that silver electrode with respect to the hydrogen electrode. And that gives you the standard reduction potential, E standard. So in this reaction, at the standard hydrogen electrode, hydrogen gas forms protons and electrons, and the potential of this is per definition 0 volts. The silver can then react with the electrons from the hydrogen gas to form solid silver, and in the standard hydrogen electrode more protons will be formed because the hydrogen gas has given away electrons. And now when you measure with the voltmeter up here the potential, you will get a positive potential. That basically means the positive potential is that the reaction proceeds spontaneously to the right, meaning to here, or to the formation of solid silver, or to the reduction of silver, because silver has, or solid silver has a higher electrochemical potential than the standard hydrogen electrode. And remember from the last slide, electrons always flow to higher electrochemical potentials, like we just stated. And that's why now we measure a positive electrochemical potential for the silver, right? So silver attracts electrons more than the hydrogen does, and therefore it is a reducing chemical in comparison to hydrogen. So the standard cell potential, as we've seen before, can now also be measured and then gives you the standard Gibbs-free energy change with respect to the hydrogen electrode. And that also gives you basically the equilibrium constant for this chemical reaction here, whether it's towards the right or towards the left, with respect to the standard hydrogen electrode. So scientists, they went to the laboratory and they measured the standard reduction potentials of all kinds of electrodes. And they tabulated these values here. So in the first column of this table, you see the reduction reaction. It's, for instance, it's always the element reacting with electrons to form the reduced version of it. And in the second column, you see the standard reduction potentials with respect to the standard hydrogen electrode, of course. You see, for all these here, these are positive standard reduction potentials. That means those chemicals here, they all are attracting electrons more than the protons in the hydrochloric acid solution of the standard hydrogen electrode do. So therefore, electrons will always flow from left to right here. But there are other elements which, with respect to the standard hydrogen electrode, have negative standard reduction potentials. And therefore, the electrodes will flow from them to the standard hydrogen electrode. So you see here, for instance, aluminium 3+ or iron 2+, they are less attractive to electrons than the protons are. Those measurements are taking place at 1 mole per liter, right? But in biochemistry, for protons, you actually have pH 7 as the standard state. So pH 7 corresponds to a proton concentration of 10 to the negative 7 mole per liter. So when you carry out this measurement in a solution of hydrochloric acid with pH 7, then you denote this not as the E standard, but as the E standard prime, right? Just for your information, so you will encounter probably this as the standard hydrogen electrode in the future. In summary, we have learned that the cell potential, delta E potential, is related to the Gibbs-free energy change of the redox reaction and the equilibrium constant K. So for instance here, the equilibrium constant K for this redox reaction here will tell you whether there is solid silver produced and protons, or whether you have silver plus and hydrogen gas. So we've seen in the previous slide, its equilibrium constant is towards the right side here, and because it has a positive standard reduction potential. So the standard hydrogen electrode allows you to determine these standard reduction potentials, which then give you information about the Gibbs-free energy change and the equilibrium constant. Thanks. In the next class, we will talk about the Nernst equation that also gives information about the concentration dependence of the reduction potentials. See you.